What if, somewhere beyond the reach of our eyes, the universe has already ended? Not everywhere. Perhaps, and not in the dramatic way stories usually imagine, but in some distant region where stars have gone dark, galaxies have vanished behind expanding space, or the fabric of reality itself has changed beyond recognition. The strangest part is that we might continue seeing that place for millions or billions of years, glowing softly in our telescopes as though nothing had happened. Before we begin, what time is it where you are? And where in the world are you listening from tonight? Now let your thoughts settle, and imagine that the night sky is not a picture of the universe as it is, but a collection of messages still travelling toward us from many different ages. When you look at the moon, you are not seeing it exactly as it is at this instant. Moonlight takes a little more than 1 second to cross the space between the moon and Earth, so the face above you belongs to the recent past. The delay is too small to notice in ordinary life, yet it reveals something fundamental. Sight is never immediate. Every image reaches you only after light has completed a journey. The same is true when you look across a room. Although the delay is unimaginably brief, nothing visible arrives without travel time. The universe does not present itself to us all at once. It arrives piece by piece, carried by light, radio waves, and other signals moving at the fastest speed nature appears to allow. The sun is farther away, so its light needs about 8 minutes to reach Earth. If the sun could somehow vanish without warning, an impossible event under known physics, but a useful thought experiment, our sky would continue to shine for those 8 minutes. Earth would also continue following its orbit for roughly the same interval, because changes in gravity do not spread instantaneously either. For a short while, everything here would proceed as though the sun still existed. The warmth on your face, the shadows on the ground, and the blue above you would all be echoes of something already gone. This does not mean the sun is in danger. It means only that information has a speed limit, and that every observer lives inside a delayed version of the cosmos. Now extend that delay outward. The nearest star system beyond the sun, Alpha Centauri, is more than 4 light-years away. The light reaching us tonight began its journey years ago. Some stars visible to the unaided eye are hundreds or thousands of light-years distant. When you see them, you are seeing ancient light that left before many events of human history had occurred. A star in the sky may have changed since that light departed. It may have brightened, dimmed, shed part of its outer layers, or, in rare cases, exploded. We would not know until the newer light finally arrived. The star would remain in our sky as a record, not of its current state, but of a chapter already completed. This is where the title's question first becomes scientifically meaningful. Could the universe have already ended somewhere else? If by ended we mean that a particular star has died, then certainly, yes. Stars are ending all the time, though their deaths are transformations rather than disappearances. Massive stars collapse and explode. Smaller stars eventually fade into dense remnants. If by ended we mean that a distant civilization, planet, or entire stellar neighbourhood no longer exists in the form we would recognize, that is also possible. Because their light takes time to arrive, we might still observe a calm and luminous past, while the present reality there has become entirely different. But the phrase, the universe, makes the question deeper. A star can end. A galaxy can be altered. A region can become cold, empty, or unreachable. Yet can the universe end in one place while continuing in another? To answer that, we have to be careful with language. The universe is not an object sitting inside a larger room. In modern cosmology, it includes space, time, matter, energy, and the physical relationships among them. So, an ending in one location may refer to local destruction, the loss of usable energy, a boundary beyond which signals cannot return. or a more exotic change in the state of space itself. These possibilities are very different, and science treats them with different levels of confidence. The easiest kind of cosmic ending is local. Imagine a planet orbiting too close to an aging star. As the star expands, the planet may be scorched, stripped of its atmosphere, or swallowed. To observers on that world, if any existed, the event could feel like the end of everything, yet the surrounding galaxy would continue. Or imagine a massive star collapsing into a black hole. Nearby matter may be heated, torn apart, or expelled in powerful jets. Again, one region changes violently while the larger cosmos remains. Nature allows endings within endings, like lights going out one by one in an immense city that has no visible edge. Galaxies themselves also evolve, though usually over timescales far longer than a human life. They collide, merge, and consume their available gas. New stars become less common as the raw material for star formation is used up or heated beyond easy collapse. In the far future, many galaxies may grow dimmer as their brightest stars disappear. This is not an abrupt death but a slow transformation. More like a fire settling into embers, a distant galaxy may one day contain mostly stellar remnants. Cold planets, black holes, and scattered particles. To us, however, the light arriving from that galaxy could continue showing an earlier era filled with young stars, luminous clouds, and vigorous change. The further we look, the more ancient the view becomes. The Andromeda Galaxy appears to us as it was roughly 2.5 million years ago because its light has crossed that vast distance before reaching Earth. When telescopes detect galaxies billions of light years away, they reveal the universe at a much younger age. Astronomers do not merely look across space, they look into cosmic history. A deep image of the sky is therefore not one frozen moment. It is a layered archive. Nearby objects are shown almost in the present, while distant ones appear in remote epochs. Every direction contains a different depth of time. There is also a limit to how far this archive can reach. The universe is about 8 billion years old. So light has had only a finite time to travel, because space itself has expanded while that light was moving. The most distant matter we can presently observe is now much farther away than 8 billion light years. Beyond the observable universe, there may be more galaxies, perhaps vastly more, but their light has not had time to reach us. We cannot see those regions directly, and we do not know their current condition. They are not necessarily unreal or empty. They simply lie beyond the boundary of the information available to us today. This layered view creates a quiet but important misunderstanding. We often imagine that the night sky is the universe spread before us at once, like a landscape seen from a hill, but a landscape is close enough that light travel time does not matter to our senses. The cosmos is different. It resembles a vast room in which every object sends its image through a different length of corridor. Some messages arrive quickly, others travel for nearly the entire age of the universe. When you look up, you are not seeing a universal present. You are receiving a mosaic assembled from countless past moments, each determined by distance and the path light has taken. For that reason, something may already have happened far away without being part of our reality yet in any practical sense. This does not mean the event is unreal. It means the information has not reached us. Physics separates events not only by where they occur, but also by whether signals can travel between them. An event on a distant world cannot influence Earth until enough time has passed for light or another causal signal to cross the gap. Until then, it lies outside our immediate causal contact. We may describe it as having happened in some coordinate system, but we cannot verify it, react to it, or be affected by it before its signal arrives. Physicists often picture this structure using what is called a light cone. Imagine yourself at the center of a widening cone made from every signal that could have reached you from the past. Events inside that cone can, in principle, leave evidence in your surroundings. Events outside it are too distant for their signals to have arrived yet. A second cone opens toward the future, marking the places your own signals might someday influence. This simple image turns the universe into a web of possible communication. It also explains why a catastrophe far away could remain unknown to us until its light enters our past cone. It has no path into our present experience. That last point leads toward a stranger idea. In everyday life, we assume there is one shared now. You and a person across the room can agree on what is happening at the same moment, across astronomical distances. However, Einstein's theory of relativity shows that simultaneity becomes more subtle. Two observers moving differently may disagree about whether distant events occurred at the same time, while still agreeing on the order of events that can causally affect one another. There is no simple cosmic clock ticking identically for every place. So the sentence, "the universe has already ended somewhere else," contains a hidden problem. The word "already" depends on how distant events are compared. We do not need to solve that problem tonight. For now, it is enough to notice that the universe resists the ordinary intuition of a single shared present. The farther apart two places are, the less meaningful it becomes to speak casually of what both are doing right now. We can choose a coordinate system and define a useful cosmic time, especially in cosmology. But nature does not provide a universal moment that every observer must agree upon. This does not make reality vague. It means reality is structured by relationships, motion, distance, and the speed at which causes can produce effects. There is comfort in this, even though it can sound unsettling. The universe does not hide the present from us out of cruelty or mystery. It simply obeys a consistent rule. Information travels. Every photon crossing the darkness is a messenger, carrying evidence of the place and time from which it came. Some have travelled through dust, curved around massive objects, or stretched to longer wavelengths as space expanded. By the time they reach a telescope, they may be faint, scattered, and ancient, yet they still tell a story. Astronomy is the art of listening carefully to those delayed stories and reconstructing a cosmos we can never observe all at once. Scientists therefore speak carefully about what is observed, what is inferred, and what remains unknown. We may see an ancient galaxy and use well-tested physical laws to estimate how it probably evolved after its light departed. We can compare it with nearer galaxies at later stages and build a coherent history. But an inference is not a direct view of its present condition. The distinction matters because science is strongest when it marks the edge of its certainty. We know that light carries the past. We know that distant regions continue to change. Yet we cannot simply look beyond the latest message and declare exactly what has happened there. So when we ask whether some distant part of the universe has already ended, the first answer is gentle and precise. Something there may indeed have changed beyond recognition. A star may have died. A planet may have frozen. A galaxy may have crossed a threshold in its evolution. Even more dramatic possibilities may exist, though we will approach them carefully. But whatever has happened, we cannot know it until nature allows the message to arrive. The sky above us is therefore both real and historical, present to our eyes yet rooted in the past, offering knowledge while preserving a quiet boundary around everything we have not yet received. As you rest beneath that sky, imagine every point of light as a letter still in transit. Some were sent years ago, some centuries ago, and some before Earth existed in its present form. They do not tell us what the whole universe is doing now, because there may be no single now to reveal. They tell us instead what the universe has been, layer after layer, distance after distance, and somewhere beyond the oldest message we have received, change continues in silence. Whether those regions are flourishing, fading, or becoming forever unreachable. Their current condition remains beyond us, waiting behind the patient speed of light. To understand how the universe can seem alive long after some distant place has changed, we need to follow the path of light more carefully. Light is not merely illumination. It is information traveling through space. Every beam carries traces of the matter that released it, the temperature of that matter, the atoms it contained, and the motion of the source. When a telescope gathers a faint glow from a remote galaxy, it is not collecting a live broadcast. It is receiving an ancient record, preserved in photons that may have crossed empty space for billions of years. The farther the source, the older the message. Distance and history become woven together, so that looking outward is also looking backward. This backward view begins close to home. Radar signals sent to Venus may take several minutes to return, depending on the planet's position. Light from Jupiter needs tens of minutes to reach us, while sunlight reflected from Pluto takes several hours. These delays are small by cosmic standards, yet they remind us that even the solar system is not seen all at once. Spacecraft engineers must plan around this. A command sent to a distant probe cannot produce an immediate answer. The machine receives the instruction later, performs its task, and then sends a reply that requires another long journey. Exploration becomes a conversation with pauses written into the structure of nature. Beyond the solar system, the pauses grow into years. A star 50 light-years away appears as it was 50 years ago. Its light may have left when different leaders governed nations, when different technologies filled human homes, and when many people now alive had not yet been born. If astronomers detect a planet circling that star, they are observing the system's past arrangement. The planet may still be there, and the star may still shine much as it did. But direct confirmation must always arrive late. The cosmos offers no instant update. It gives us evidence delayed by distance, and asks us to reconstruct the present with patience. Astronomers call the interval between emission and observation the look-back time. It sounds simple, but it is one of the most powerful ideas in cosmology. A galaxy seen with a look-back time of 1 billion years is shown not merely far away, but 1 billion years younger than it would be in our chosen cosmic frame today. By comparing galaxies at different look-back times, scientists can arrange observations into something like a family album of the universe. No single galaxy is watched continuously from birth to old age. Instead, many galaxies are observed at different stages, allowing patterns of growth, collision, star formation, and fading to emerge. This method resembles walking through a forest where distance also corresponds to age. Nearby trees might appear mature, while those farther away seem progressively younger, not because the forest is arranged that way in reality, but because the light from distant trees takes longer to reach you. In the actual universe, nearby and distant galaxies all continue to evolve, yet our view places them on different pages of history. The most remote galaxies we detect are often seen as small, irregular, and intensely active, because their light began travelling when the cosmos itself was young and galaxies were still assembling their structures. Light contains more than an image. When separated into a spectrum, it reveals dark and bright lines produced by atoms and molecules. Hydrogen leaves one pattern, oxygen another, and each element marks light in a recognizable way. From these fingerprints, astronomers can learn what distant stars are made of without touching them. They can estimate temperature, density, magnetic fields, and chemical abundance. They can also measure motion. If a source moves away, its light shifts toward longer, redder wavelengths. If it approaches, the light shifts toward shorter, bluer wavelengths. Thus, an ancient photon carries both a portrait and a history of movement. On the scale of the universe, redshift has another cause as well. Space expands. And as light travels through expanding space, its wavelength is stretched. A photon that began as visible or ultraviolet light may arrive as infrared radiation after billions of years. The farther it has travelled through cosmic expansion, the greater this stretching can become. Astronomers use redshift as one clue to distance and cosmic age. Though the relationship must be interpreted through a model of expansion, the changing wavelength does not mean light grows tired in an ordinary sense. It means the geometry through which it moves has evolved during the journey. This expansion complicates simple ideas of distance. You may hear that a galaxy is 13 billion light-years away because its light travelled for about 13 billion years. Yet during that journey, space continued expanding. So the galaxy's present distance can be much larger. The light left when the galaxy was closer, crossed a changing universe, and reached us only after the intervening space had stretched. Cosmologists distinguish between look-back time, light travel distance, and present-day distance because each answers a different question. These distinctions are not merely technical. They remind us that cosmic history unfolds in a universe whose stage is itself changing. Telescopes are designed to collect these old signals, often far too faint for human eyes. A larger mirror gathers more photons, just as a wide bowl catches more rain. Long exposures allow the telescope to accumulate light over minutes, hours, or even days. What appears empty to the eye may slowly reveal thousands of galaxies. Each small patch of glow can contain billions of stars, and each is seen at its own distance and time. Deep astronomical images are therefore crowded not only with objects, but with eras. They compress vast stretches of cosmic history into a single quiet frame. Different telescopes listen to different kinds of light. Radio telescopes detect long wavelengths from cold gas, energetic particles, and distant cosmic structures. Infrared observatories can see through dust and receive the stretched light of very remote galaxies. Visible light telescopes reveal stars and glowing clouds familiar to the eye. Ultraviolet and X-ray instruments uncover hotter, more violent environments around young stars, supernova remnants, and black holes. None of these views is complete alone. Together they form a layered record, as though the universe had written its history in many alphabets and asked us to read them side by side. Each band reveals a different layer of activity hidden within the same quiet sky. There are messengers beyond light, neutrinos, nearly massless particles that rarely interact with matter, can escape from dense stellar interiors that photons cannot immediately leave. Gravitational waves carry ripples produced by accelerating masses, especially the mergers of black holes and neutron stars. These signals also travel at the speed of light, as far as measurements show, and they too arrive after a delay. When several kinds of messenger are detected from the same event, astronomers gain a richer account. One signal may reveal the motion of matter, another the release of energy, and another the creation of heavy elements. Together, these messengers let us hear events that no ordinary image could fully describe. A supernova offers a beautiful example of delayed knowledge. When a massive star collapses, neutrinos may escape from the core before visible light breaks through the surrounding layers. Detectors on Earth can receive a brief burst of neutrinos, followed later by the brightening of the star. Yet both messages still describe an event that happened long ago at the source. If the star is thousands of light-years away, the explosion occurred thousands of years before the alert reaches our instruments. For us, the event feels new because the information is new. In the star's own region, it belongs to an ancient past. This difference between the age of an event and the age of our knowledge is one of astronomy's quietest wonders. News on Earth is considered old after days or weeks. Cosmic news may arrive millions of years after the event and still be called a discovery. The word new refers not to when nature acted, but to when evidence entered human awareness. A newly observed galaxy may be among the earliest structures ever formed. A newly detected collision may have occurred before our species existed. Astronomy continually receives ancient events as fresh experience, turning the universe into a delayed conversation across immense darkness. The oldest light we can observe directly is the cosmic microwave background. It was released when the universe was about 380,000 years old. After matter cooled enough for electrons and atomic nuclei to combine into neutral atoms, before that transition, light scattered constantly from charged particles, and the cosmos was opaque, more like a glowing fog than a transparent sky. Once atoms formed, photons could travel freely. Those photons have crossed the expanding universe ever since, stretched into microwaves, and now arrive from every direction as a faint afterglow of the early cosmos. It is an ancient horizon of visibility, not a picture of creation itself. When instruments map this background, they are not seeing the absolute beginning. They are seeing the oldest surface from which light could travel freely to us. Beyond that surface lies an earlier era that ordinary telescopes cannot reveal through electromagnetic radiation. Scientists study it indirectly through theory. Particle physics, the patterns in the microwave background, and possible signals such as primordial gravitational waves, which have not yet been confirmed. Even our deepest view, therefore, meets a boundary. The universe has a visible history, and behind it a more hidden history whose traces must be inferred rather than photographed. The earlier universe survives for us mainly through subtle patterns impressed upon later light and matter. This boundary also means that the observable universe is not the same as the whole universe. Our observable region is defined by the distance light has been able to travel since the early cosmos became transparent, adjusted for expansion. Another observer in a galaxy far away would have a different observable sphere centered on that galaxy. The two spheres might overlap greatly, or only partly, depending on their separation. Neither observer occupies a privileged center of all existence. Each stands at the center of a personal horizon created by time, distance, and the finite speed of information. Every location, therefore, carries its own window onto cosmic history, limited but still extraordinarily rich. Now imagine a galaxy so distant that we see it as it appeared when the universe was less than 1 billion years old. Its light has travelled across most of cosmic history. During that time, the galaxy itself may have merged many times, formed countless generations of stars, grown a central black hole, and become part of a much larger structure. The delicate object in our telescope may no longer exist in that form, yet its earlier state remains preserved in the light that reaches us. The image is not false. It is accurate to a time we can no longer visit. What has ended is the form we can observe, not necessarily the matter from which it grew. This is why astronomers speak of observing evolution without watching any single object evolve over billions of years. They compare populations across time. Nearby galaxies show the relatively recent universe. More distant galaxies show earlier periods. By studying many examples, researchers can infer how typical galaxies changed, while recognizing that individual histories vary. It is similar to understanding human aging by meeting people of many ages rather than following one person for a century. The comparison is imperfect, but it reveals how snapshots can become a story when guided by physical laws and large collections of evidence. Through patient comparison, the lives of galaxies become legible without ever becoming directly complete. Those physical laws are tested nearby and then applied carefully to distant times. Gravity shapes galaxies. Nuclear reactions power stars. Atomic transitions create spectral lines. Relativity governs the movement of light through curved and expanding spacetime. Scientists assume that these laws have remained broadly consistent because distant observations fit them remarkably well. Yet they also search for deviations, because a genuine change in a fundamental constant or an unexpected pattern could transform our understanding. So far, evidence supports deep continuity across cosmic history. But every conclusion carries measured uncertainty rather than absolute philosophical proof. Because observation is always delayed, we can never place a telescope outside time and see the entire universe at one instant. We can build a model of cosmic history, choose a useful definition of cosmic time, and calculate what distant regions may be like today. These models can be extremely successful. They predict the abundance of light elements, the growth of structure, and the pattern of the microwave background. Still, the present state of a remote galaxy is not directly visible until its present light arrives. And for some galaxies, cosmic expansion may prevent that light from ever reaching us. This possibility leads toward a more profound kind of disappearance. A galaxy need not be destroyed to vanish from our future view. If space between us expands quickly enough, newer light from that galaxy may never overcome the growing distance. We may continue receiving older and older portions of its history for a time, while its later story becomes permanently inaccessible. The galaxy still exists somewhere in the broader cosmic picture, but it crosses beyond our horizon of future communication. From our perspective, it fades not because its stars go out, but because the universe carries its messages away from us. It becomes an ending of contact rather than an ending of existence. There is a softness to this kind of ending. No explosion marks the boundary. No wall appears in the sky. The connection simply weakens as wavelengths stretch and signals grow faint. Eventually, information that might once have reached us no longer can. The universe becomes divided into regions that share a past but cannot share an indefinite future. Galaxies once visible to one another may slip beyond mutual contact as expansion continues. Their histories separate, not through violence, but through geometry, each region enclosed by its own widening silence. Silence here is not emptiness, but the absence of any remaining path between once connected places, so the light arriving tonight is precious in a very literal sense. It may be the only version of a distant place that the universe will ever allow us to receive. Every photon is a surviving piece of causal contact, a small bridge across time. Some bridges lead to stars that have changed. Some lead to galaxies whose future is hidden. Some carry the afterglow of an era before stars existed at all. By collecting these messengers, astronomy does more than create images. It preserves relationships between parts of the cosmos that distance and expansion are slowly transforming. And as you listen in the quiet, you might picture the observable universe not as a sphere filled with objects, but as a vast archive made of arriving signals. Near the center are recent pages from nearby space. Farther out, the pages grow older, until they reach the pale boundary of the cosmic microwave background. Beyond that boundary, reality continues, but ordinary light no longer gives us a direct view. The archive is incomplete, yet it is enough to reveal a universe with a history, a childhood, and an unfolding future whose distant chapters may already be written beyond our sight. The question now becomes stranger. If distant places are always seen in the past, what do we really mean when we say that something has already happened there? In daily life, now feels obvious. A clock ticks, a room is shared, and people agree that one event is happening while another is still ahead. But across the immense distances of the universe, the idea of a single present moment begins to loosen. Einstein's theory of relativity does not tell us that reality is unreal or confused. It tells us that space and time are connected, and that observers moving differently may divide the same set of events into past, present, and future in different ways. The farther apart the events are, the more noticeable this difference can become. To see why, imagine two flashes of light occurring at opposite ends of a very long train. An observer standing exactly halfway along the platform sees both flashes arrive at the same time and concludes that they happened simultaneously. But an observer inside the moving train is travelling toward one flash and away from the other. The light still moves at the same speed for both observers, yet the passenger receives one flash before the other. From the passenger's point of view, the events were not simultaneous. Neither observer is making a mistake. They are using different states of motion, and relativity requires them to assign different time coordinates to distant events. This is called the relativity of simultaneity. It is not mainly about clocks being poorly synchronized or signals arriving late. Those practical delays can be corrected. The deeper point is that after every correction is made, observers moving relative to one another can still disagree about which distant events share the same now. They will agree about events that occur at the same place and about any sequence linked by cause and effect. If one event sends a signal that later produces another, everyone agrees on the order. But for widely separated events that cannot influence each other in time, nature does not supply one universal verdict about which happened first. Consider Earth and a hypothetical planet hundreds of light years away. At this moment, you may choose a coordinate system in which a certain event on that planet is happening simultaneously with your listening here. An astronaut moving rapidly relative to Earth might use an equally valid coordinate system in which that distant event has already happened. Another astronaut moving the opposite way might describe it as still lying in the future. This does not permit anyone to change the event or receive information from it faster than light. The disagreement concerns how distant, causally disconnected events are labelled, not what any observer can actually witness or control. That distinction protects relativity from becoming a license for fantasy. No observer can simply choose a coordinate system and make a star explode. No one can learn the result of a distant event before its signal arrives. Coordinates are ways of organizing space-time, not forces acting upon it. What changes between observers is the division of distant events into simultaneous slices. What remains fixed is the network of causal relationships. Light cones preserve that network. If an event lies inside your past light cone, it can have influenced you. If it lies inside your future light cone, you may eventually influence it. If it lies outside both, no signal travelling at or below light speed can connect you yet. Events outside one another's light cones are described as space-like separated. For such events, different observers may disagree about their order without contradiction. Suppose one distant galaxy experiences a supernova while another galaxy, extremely far away, forms a new star. If no light or causal influence could travel between the two events in time, one observer might say the supernova came first, another that star formation came first, and a third that they occurred simultaneously. None of these descriptions changes what happened locally. The newborn star still forms from collapsing gas. The massive star still dies. Only the attempt to place both events on one universal timeline becomes observer-dependent. In contrast, events connected by a possible signal are time-like or light-like separated. If a star explodes and its light later reaches Earth, every observer agrees that the explosion occurred before the detection. They may calculate different durations or distances depending on their motion, but they cannot reverse cause and effect. This agreement is crucial. Relativity reshapes time without destroying order, where order matters physically. The universe may lack a universal present, yet it still possesses a reliable causal structure. Causes remain before their effects. Information remains limited by the speed of light, and no ordinary observer can receive an answer before the question has physically been sent. This brings us back to the phrase, "the universe has already ended somewhere else." If we mean that a distant region underwent some ordinary physical change and its signal is travelling toward us, then there may be coordinate systems in which the change is assigned a time earlier than our present. But until its signal arrives, the event is outside our direct knowledge. And if the region is so far away that no signal can ever reach us, the word already becomes even less secure. We can describe the event within a cosmological model, but we cannot point to a universal cosmic clock and say that all observers must agree it has occurred now. Cosmologists nevertheless often speak of the age of the universe and of events happening at particular cosmic times. This is not careless. On very large scales, the universe appears approximately homogeneous and isotropic, meaning that matter is distributed in broadly similar ways when averaged over enormous distances, and that no direction is fundamentally preferred. This structure allows scientists to define a useful family of observers who move with the overall cosmic expansion. Clocks carried by these observers provide what is called cosmic time. In that framework, the universe has an age of about 13, 8 billion years, measured from the hot, dense early state described by modern cosmology. Cosmic time is extraordinarily useful, but it is not the same as an absolute time built into all possible observations. It belongs to a preferred description suggested by the large-scale distribution of matter. An observer moving rapidly relative to the cosmic expansion would measure time differently along their own path. Near massive objects. Gravity also affects the rate at which clocks tick. Still, for describing the history of galaxies, the cooling of the early universe, and the growth of cosmic structure, cosmic time provides a natural shared language. It lets researchers say that certain processes occurred when the universe was a particular age, while remaining consistent with relativity. You can imagine cosmic time as a set of gentle layers through the expanding universe. One layer may correspond to the era when the first stable atoms formed. Another may mark the period when the first stars appeared. Later layers contain mature galaxies, planets, and eventually life on Earth. These layers are not universal in the strict Newtonian sense. Yet within the standard cosmological model they organize large-scale history elegantly. The idea is similar to defining sea level on a rough planet. The surface is not perfectly simple everywhere, but it provides a useful reference from which local heights can be measured. Before Einstein, time was commonly imagined as an invisible river flowing at the same rate everywhere. Space formed a separate stage, and events happened upon it as one universal clock advanced. Relativity replaced this picture with space-time, a four-dimensional structure in which space and time are interwoven. An object does not merely move through space while time passes independently. It follows a path through space-time called a world line. The amount of time measured along that path depends on motion and gravity. Each observer carries their own clock, and that clock records what physicists call proper time, the time experienced along that particular journey through the universe. Proper time is deeply personal but not subjective in the ordinary sense. A clock travelling with you measures your proper time, and everyone can agree on what that clock records when reunited with it. Two clocks that follow different paths through space-time may accumulate different amounts of time. This has been measured with precise clocks on aircraft and satellites. It is also essential to technologies such as satellite navigation, where both motion and gravity alter clock rates enough to require correction. Relativity is not an abstract puzzle reserved for distant galaxies. Its effects are quietly included in systems used every day. The famous twin scenario makes this easier to picture. One twin remains on Earth while another travels at high speed and later returns. The travelling twin follows a different path through space-time and experiences less elapsed time. The difference is not caused by a mechanical failure in either clock. It arises from the geometry of space-time. At ordinary speeds, the effect is tiny. Near the speed of light, it becomes dramatic. A traveller could cross great distances while aging less than people who remain behind, though the energy and engineering required would be immense. Time, in this sense, is not a single quantity shared identically by all journeys. Gravity changes time as well. According to general relativity, clocks deeper in a gravitational field run more slowly relative to clocks farther away. Near Earth, the effect is small but measurable. Near a neutron star or black hole, it can become much stronger. To a distant observer, a clock descending toward a black hole's event horizon appears to slow. To the falling traveller, their own clock continues normally, though the surrounding environment may become deadly. Again, there is no contradiction. Different paths and positions through curved space-time accumulate time differently, and each local clock remains perfectly ordinary to the observer travelling beside it. These effects matter when imagining endings near extreme objects. A distant observer may see matter approaching a black hole become redder, dimmer, and apparently slower, never quite watching it cross the horizon in ordinary external coordinates. The falling matter, however, crosses the horizon after a finite amount of its own proper time. Assuming the black hole is large enough that tidal forces do not destroy it first, which account is real? Both describe the same space-time from different perspectives. The event horizon is not a place where time simply stops. It is a boundary beyond which signals can no longer return to the exterior universe. A black hole, therefore, provides another example of how an ending can depend on the question being asked. From outside, information from the infalling object becomes increasingly delayed and weakened. From the object's own perspective, crossing occurs without an infinite wait. After crossing, every future directed path leads farther inward, at least according to classical general relativity. The object's ability to communicate with the outside has ended, even though its local passage through time continues. Whether information is ultimately lost in black hole evaporation is a deeper problem involving quantum theory, and physics has not yet produced a complete, experimentally confirmed answer. At the largest scales, we encounter a similar tension between local experience and global description. Every observer occupies a definite location and moves along a definite world line. Around them, light arrives from different eras. Cosmology then constructs a broader model linking these observations into a history of the expanding universe. The model may define a present cosmic time, but no observer can directly see that entire cosmic slice. Each sees only the past light cone, a tapered record of events whose signals have arrived. The universe described by theory is therefore always larger than the universe displayed in observation, with unseen regions inferred from consistent laws and patterns. This may feel like a limitation, but it is also what makes cosmology intellectually beautiful. Scientists do not receive a complete view. They infer the hidden structure from patterns in incomplete signals, the expansion of space, the abundance of elements, the growth of galaxies, and the afterglow of the early universe all fit together into a coherent account. Yet the account remains open to revision wherever evidence is uncertain. Relativity teaches humility without demanding confusion. It says that some familiar words, especially now, must be used carefully when stretched across cosmic distances, because language formed on Earth was never designed for the geometry of the whole cosmos. So has the universe already ended somewhere else? At this stage, the most accurate reply is that the question contains several possible meanings. Local systems have certainly ended or transformed beyond recognition. Some events may be described as already occurring in one coordinate system and not yet occurring in another. Certain regions may be permanently unable to exchange signals with us, but none of this means that an invisible universal clock has recorded a secret catastrophe while Earth waits for the news. Modern physics offers no single presence spread across all of space in the simple way ordinary intuition suggests. Instead, reality unfolds locally. Stars burn in their own neighborhoods. Planets move along their paths. Galaxies evolve within clusters and filaments. Each region exchanges influences with nearby regions. While information moves outward at finite speed, the larger universe emerges from this vast network of local events, connected where signals can pass and separated where they cannot. There is no need for every place to share one instantaneous moment. The cosmos remains ordered through causality, even when simultaneity dissolves, and every event occupies its own quiet position within the wider structure of space-time. As you rest, imagine space-time not as a rigid stack of universal moments, but as an immense woven fabric of journeys. Every star traces a line, every planet follows another, Every photon draws a bright thread between a mission and arrival. Your own life is one quiet world line among them, carrying its own measured time through the night, far away. Other events continue along paths that may never intersect yours. They do not need to share your present to be real. And perhaps the universe is most peaceful when viewed this way, not as a single clock rushing toward one ending, but as countless local histories unfolding within one deep and connected geometry. Once we separate the idea of a universal ending from the many smaller endings that occur within the cosmos, the universe becomes less like a single object approaching one final moment and more like an immense landscape of transformation. Stars are born, shine, and die. Planets form, cool, collide, or drift into darkness. Galaxies merge and gradually exhaust the gas from which new stars can be made. In one region, creation may be vigorous, while somewhere else the same processes have nearly ceased. These are not endings of existence itself. They are endings of structure, habitability, communication, or complexity. To understand whether the universe can end somewhere else, we must first understand how many different meanings the word end can quietly contain. A star's death is among the clearest cosmic endings, though even here nothing simply disappears. The fate of a star depends mostly on its mass. A star like the Sun spends billions of years converting hydrogen into helium in its core. When the hydrogen becomes scarce, the core contracts while the outer layers expand, turning the star into a red giant. Eventually, those outer layers drift away, leaving behind a dense white dwarf. The star has ended as a shining source powered by nuclear fusion, but its matter remains. The expelled gas may enrich space with heavier elements, while the white dwarf slowly cools over timescales far longer than the present age of the universe. More massive stars follow a more violent path. Their cores grow hot enough to fuse progressively heavier elements until iron accumulates. Fusing iron does not release usable energy in the same way, so the core can no longer support the weight above it. Collapse follows in a fraction of a second. The outer layers may be blasted into space in a supernova, while the core becomes a neutron star or, if massive enough, a black hole. For nearby planets, such an event can be devastating. Radiation may strip atmospheres or alter chemistry, yet the explosion also creates and disperses elements essential for planets and life. In the cosmos, destruction and renewal are often different chapters of the same physical process. A planetary system can also reach its own ending without any dramatic stellar explosion. As a star brightens over time, a once temperate planet may become too hot for liquid water. Its oceans may evaporate. Its atmosphere may change. And any surface life may lose the conditions it depends upon. Later, the star may expand and engulf inner planets entirely. Farther worlds might survive physically while becoming frozen, dark, and isolated. Whether such changes count as an ending depends on what is being measured. The planet may remain, but its biosphere could be gone. Its geology may continue, while its capacity to support complexity quietly closes. Life itself has experienced many endings on Earth, though not the complete ending of life as a whole. Mass extinctions have erased large fractions of species, reorganizing ecosystems and opening new evolutionary paths. These events remind us that endings in nature are often selective. One lineage disappears while another expands. One biological world collapses while a different one slowly emerges. If distant planets host life, their histories may contain similar thresholds shaped by climate. Impact events, stellar activity, or internal geological change. We do not yet know whether life is common, rare, fragile, or remarkably persistent. The silence of the sky does not tell us enough to choose among these possibilities. On larger scales, Galaxies experience endings that unfold over billions of years. A galaxy forms stars when cold gas gathers into dense clouds and collapses under gravity. But this process cannot continue at the same rate forever. Gas is consumed, expelled by stellar winds, heated by explosions, all prevented from cooling by energetic activity around a central black hole. Over time, star formation may decline. The galaxy does not vanish. Its older stars continue orbiting, and its structure may remain visible for an immense period. Yet one of its defining creative processes slows, then nearly stops. Astronomers sometimes call such galaxies quenched, a word that suggests a fire no longer being fed. Galaxy clusters can accelerate this quiet decline. As a galaxy falls through the hot gas filling a cluster, pressure can strip away its own supply of star-forming material. Gravitational encounters can disturb its shape or remove stars. Repeated interactions may transform a spiral galaxy rich in gas into a smoother system dominated by older stars. These changes are not usually sudden from a human perspective. They unfold across timescales so vast that no observer could watch them directly from beginning to end. Yet by comparing many galaxies in different environments, astronomers can reconstruct the pattern. The cosmos contains entire populations moving from luminous youth toward a slower and dimmer age. Black holes create another kind of ending by severing communication. An object that crosses an event horizon cannot send a signal back to the outside universe. According to classical general relativity, from the exterior perspective, that object has entered a region permanently hidden from view. This does not necessarily mean it has ceased to exist. Its mass and other measurable properties contribute to the black hole, but its detailed future becomes inaccessible. The event horizon is therefore an ending of causal contact. It marks a boundary beyond which stories may continue locally, yet no later chapter can be returned to distant observers. The centers of galaxies can host black holes millions or billions of times the Sun's mass. When gas falls toward them, it forms hot, rapidly rotating disks and can release enormous amounts of radiation. Powerful jets may extend far beyond the host galaxy. This activity can heat surrounding gas and suppress new star formation, helping push the galaxy toward quiescence. The black hole does not consume the entire galaxy like a cosmic vacuum cleaner. Most stars orbit far away and remain safe. Its influence is subtler, working through gravity, radiation, and energetic outflows. A small central region can shape the fate of an object spanning tens of thousands of light years. Collisions between galaxies may sound like endings, but they are usually transformations. Because stars are separated by immense distances, direct, stellar collisions are unlikely even when two galaxies pass through one another. Their gravitational fields reshape the systems, pulling out streams of stars and compressing gas into new regions of star formation. Over time, the galaxies may merge into one larger structure. Their original identities become difficult to distinguish. One could say that two galaxies have ended, or that a new galaxy has begun. Nature offers no sharp boundary between those descriptions. It provides continuous physical change, while human language chooses where one story closes and another begins. Even entire groups of galaxies can become isolated from the wider universe. Cosmic expansion is accelerating, apparently driven by something we call dark energy, though its fundamental nature remains unknown. On sufficiently large scales, distant galaxies recede from us faster and faster as space expands between us. This does not mean they locally move through space faster than light. Rather, the distance created by expanding space can grow at an effective rate greater than light speed without violating relativity. Over extremely long periods, more galaxies will cross beyond our event horizon, meaning signals emitted after some point will never reach us. Their existence may continue, but their future will no longer belong to our observable cosmos. For observers in the far future, This disappearance could transform the appearance of the sky. Galaxies outside the gravitationally bound local group may fade beyond detection. The descendants of the Milky Way and Andromeda, likely merged by then, could appear surrounded by darkness. Evidence of cosmic expansion may become much harder to recover. Future astronomers might see only their local stellar population and conclude that the universe is smaller and more static than it truly is. The universe would not have ended around them, yet much of its visible history would have slipped away. Knowledge itself can have a cosmic horizon, shaped not only by what exists, but by what remains observable. There are more speculative ways in which a region might end. One involves the possibility that a star passes too close to a massive black hole and is torn apart by tidal forces. Another involves the collision of neutron stars, producing intense radiation and creating many heavy elements. Gamma-ray bursts can release vast energy in narrow beams, and if one occurred sufficiently close and pointed toward a planet, it could damage an atmosphere. These events are real and observed, though their effects depend strongly on distance and direction. They are rare on human timescales, and they do not represent threats to the entire universe. They reveal instead how local catastrophe can coexist with cosmic continuity. A more profound possibility emerges from quantum field theory. In modern physics, empty space is not simply nothing. It contains fields, and those fields can occupy different energy states. The vacuum we inhabit may be the lowest possible energy state, in which case it is stable. But some theoretical models allow the possibility that it is only metastable, like a ball resting in a shallow valley with a deeper valley somewhere beyond a barrier. In that picture, space could potentially transition to a lower energy state. This idea is called vacuum decay. It is mathematically serious, but it has never been observed, and there is no evidence that such a transition is imminent. If vacuum decay were possible, it might begin in a tiny region through a quantum process and form a bubble of a new vacuum state. The bubble could then expand outward near the speed of light. Inside it, the values of physical fields might differ. Particle mass, force, and the stability of atoms could change. The structures familiar to us might no longer be possible, because the boundary would travel almost as fast as any warning signal. Observers would receive no advance notice. The first indication would also be the arrival of the transformation itself. This scenario is one of the rare cases in which the universe ending somewhere else could mean that the basic rules of a region have changed. Yet, even here, careful language is essential. Scientists do not know whether our vacuum is metastable, how long it would survive if it were, or whether known calculations remain valid under all relevant conditions. Measurements related to the Higgs field and other particles allow theoretical estimates, but uncertainties remain, and unknown physics could alter the conclusion. Some models suggest extreme longevity, far beyond the current age of the universe. Others make the vacuum completely stable. Vacuum decay is therefore not a prediction that a catastrophe is happening somewhere tonight. It is a possibility arising from incomplete theories, useful because it reveals how deeply the nature of empty space is connected to the existence of matter. There is also an important limit to what vacuum decay would mean globally. If a bubble began beyond our cosmic event horizon, its boundary might never reach us because the expansion of space could keep the regions permanently separated. In that case, one part of a broader universe could enter a new state, while our region continued unchanged. Whether it makes sense to call that the end of the universe depends on whether the whole cosmos is treated as one connected physical domain. For observers inside the bubble, familiar reality might be gone. For observers beyond causal contact, nothing detectable would happen. The same event could be ultimate locally and irrelevant elsewhere. This possibility illustrates a recurring theme. Cosmic endings are defined by boundaries. The boundary between fusion and stellar remnants, between habitability and sterility, between active galaxies and quenched ones, between communication and horizons. or between one state of a field and another. The universe rarely supplies a clean final curtain. Instead, systems cross thresholds. Afterward, certain futures are no longer available. A star can no longer return to its youthful phase. A planet may no longer support oceans. A signal beyond an event horizon can no longer reach home. An ending is often the closing of possibilities rather than the disappearance of all matter. Even the long-term future of ordinary matter is uncertain. Some theories predict that protons may eventually decay, but no proton decay has ever been observed, and experiments have established that if it occurs, the lifetime must be extraordinarily long. If protons are stable, remnants of matter may persist indefinitely in altered forms. If they decay, atoms and stellar remnants would gradually dissolve over unimaginable timescales. Black holes are also expected, according to quantum calculations, to emit Hawking radiation and evaporate. Though this process has not been directly observed in astrophysical black holes, the timescales involved are so enormous that the present universe is still extraordinarily young by comparison. The far future may therefore consist not of one sudden ending, but of a sequence of quieter transitions. Star formation declines. Existing stars burn out. Remnants cool. Gravitational systems reorganize. Black holes dominate some regions, then perhaps slowly evaporate. Useful energy becomes increasingly difficult to gather as matter, and radiation spread toward equilibrium. This broad idea is known as heat death. Though the phrase can be misleading, it does not describe a universe becoming hot. It describes a universe approaching a state in which energy differences capable of performing work have largely faded. Change may continue, but organized complexity becomes harder to sustain. Heat death, if it is the correct long-term outcome, would not occur everywhere at one synchronized moment. Different regions would exhaust their opportunities at different times. Bound systems would follow their own histories. Black holes of different masses would evaporate on different timescales. Rare fluctuations might still occur. The universe would not strike midnight and become still. It would gradually approach a state of greater uniformity, with fewer accessible sources of free energy. The ending would be asymptotic, approached more like a horizon than a wall. There may never be a single final event that could be marked on a clock, and so the universe may already contain countless endings without being ended. A star has collapsed somewhere whose light has not reached us. A planet has lost its oceans while we still see the earlier glow of its sun. A galaxy has crossed beyond communication, leaving only ancient images behind. Perhaps, in some causally disconnected region, space has entered a state unlike our own, though we have no evidence that this has occurred. Each possibility carries a different degree of certainty. From well-observed stellar death to highly speculative vacuum decay, science holds them apart, not to diminish wonder, but to protect it from confusion. As the night grows quieter, imagine the cosmos as a field of lanterns at many stages of burning. Some have just been lit. Some are steady and bright. Some have become embers. And some are hidden beyond hills from which no light will ever return. The darkness between them is not one universal ending. It is distance, time, geometry, and the gradual transformation of physical systems. Somewhere, a star is beginning. Somewhere else, one is collapsing. Elsewhere, a galaxy is fading into stillness. The universe continues not because nothing ends, but because ending and beginning are woven together across scales too vast for any single observer to witness at once. Among all the possible endings we have considered, vacuum decay is perhaps the most difficult to imagine because it does not begin with a star, a planet, or even a galaxy. It begins with empty space itself. In everyday language, a vacuum means an absence, a place where matter has been removed. In modern physics, however, empty space is not truly featureless. It is filled with quantum fields, and every particle we know can be understood as an excitation of one of those fields. Even when no particles are present, the fields remain. They possess a lowest available state, and that state determines many of the basic properties of the universe around us. You can picture a field as something extending everywhere, like an invisible ocean that fills all of space. A particle is then not a tiny solid bead floating independently, but a localized ripple in that ocean. Different fields produce different kinds of ripples. There is an electromagnetic field associated with photons, electron fields associated with electrons, and quark fields associated with the particles inside protons and neutrons. The Higgs field is especially important because its interaction with other fields helps determine the masses of elementary particles. Empty space, therefore, has structure. The state of its fields influences whether atoms can exist, whether stars can burn, and whether chemistry can unfold. A vacuum state is the arrangement of those fields when they contain as little usable energy as possible under the laws that apply. If that state is truly the lowest possible state, it is called a true vacuum and should be stable. But a field might instead rest in a local minimum, a state lower than its immediate surroundings but not the lowest state available overall. This is called a false vacuum. Imagine a marble lying in a shallow hollow on the side of a mountain. It appears settled and may remain there for a very long time, even though a deeper valley exists beyond a nearby ridge. The marble is stable against small disturbances, but not necessarily stable forever. The analogy is useful. Though quantum fields do not behave exactly like ordinary marbles, in classical physics, the marble would need enough energy to climb over the ridge before reaching the deeper valley. In quantum mechanics, there is another possibility. A system can sometimes pass through a barrier rather than over it, a process known as quantum tunneling. This does not mean the system follows a hidden ordinary path. It means the quantum description assigns a small probability that the field will appear on the other side of the barrier. If the vacuum of our universe were metastable, such tunneling could, in principle, produce a tiny region in a lower energy state. That tiny region would be the beginning of a vacuum bubble. Inside the bubble, the field would occupy the deeper state. Outside it, the old vacuum would remain. The boundary between them would contain energy and behave according to the equations governing the fields involved. Whether the bubble grew or collapsed would depend on a balance. Creating the boundary costs energy, while converting the interior to a lower energy vacuum can release energy. A very small bubble might disappear. A bubble larger than a certain critical size could become energetically favored and begin expanding. This is the basic theoretical picture, though the details depend on the underlying model. If such a bubble began expanding, its wall could accelerate to a speed extremely close to the speed of light. That detail makes the scenario uniquely unsettling, although there is no reason to believe it is imminent. Any warning would also have to travel at or below light speed. The bubble wall itself would arrive almost as quickly as the information announcing it. There would be no distant flash followed by a long interval for preparation. The first physically meaningful contact with the event would be the event. Yet from the perspective of science, this dramatic feature is less important than the deeper question of what the new vacuum would actually do to the laws governing matter. Inside a different vacuum state, the values of certain fields could change. If the Higgs field settled into a different value, the masses of elementary particles might be altered. Electrons could become heavier or lighter. Quarks might interact differently. The balance that allows protons, neutrons, and atomic nuclei to remain stable could be disturbed. Electromagnetism, nuclear forces, or the behavior of space-time might no longer support familiar structures. Atoms could fail to form, or existing matter could be rearranged into unfamiliar states. Scientists cannot describe one universal outcome because different theoretical models lead to different possibilities. The common theme is that ordinary chemistry might no longer survive. This would not be an explosion in the usual sense. An explosion releases energy into a space whose physical rules remain unchanged. Vacuum decay would change the state of the space through which everything exists. The bubble would not merely sweep objects aside like a shock wave. It could alter the conditions that make those objects possible. A planet, a star, and a living cell are all organized patterns held together by stable relationships among particles and forces. If those relationships changed, the patterns might cease to have meaning. Matter would not necessarily vanish into nothing, but it might be transformed so completely that no familiar structure remained. The possibility enters discussion partly because of what physicists have learned about the Higgs boson and the Higgs field. Measurements of the Higgs boson's mass, together with measurements of the top quark and other quantities, allow scientists to estimate how the Higgs field's potential energy may behave at extremely high field values. Within the standard model of particle physics, some calculations suggest that our present vacuum could be metastable rather than absolutely stable. But the conclusion is sensitive to measurement uncertainties, especially the exact properties of the top quark, and to assumptions about physics at energies far beyond those reached by current experiments. Unknown physics could change the picture entirely. The standard model describes known particles and forces with remarkable success, but it does not include a complete quantum theory of gravity. It does not explain dark matter, the origin of the matter-antimatter imbalance, or several other major mysteries. New particles or interactions could reshape the Higgs potential and make the vacuum more stable, less stable, or fundamentally different from the simplified calculation. For this reason, physicists do not treat metastability as an established fact. It is an intriguing possibility within an incomplete framework, not a confirmed property of the universe. Even calculations that allow metastability generally suggest that the expected lifetime of our vacuum may be enormously longer than the current age of the universe. The exact estimates vary and depend on assumptions, but the central point is that no known observation indicates an approaching transition. The universe has existed for billions of years while producing extreme environments, powerful cosmic rays, black holes, neutron stars, and violent collision. None has triggered an observed vacuum bubble. This does not logically prove absolute stability, yet it provides no practical reason to regard vacuum decay as an immediate danger. It belongs to the study of fundamental possibility, not to ordinary risk. Particle accelerators sometimes become part of public fears about this subject, but known evidence gives no reason to think they can trigger vacuum decay. Nature produces particle collisions at energies equal to or greater than those achieved in human machines. Cosmic rays have struck Earth, the Sun, neutron stars, and other bodies for immense periods. If ordinary high-energy collisions could easily initiate a destructive vacuum transition, the universe would likely have revealed that vulnerability already. Scientific safety studies have examined such concerns in detail. The continued existence of dense astronomical objects offers especially strong evidence that accelerator experiments do not create the proposed catastrophe. There is also a subtle relationship between vacuum decay and the early universe. Many cosmological models suggest that fields underwent transitions as the universe expanded and cooled. The behavior of matter changed as symmetries were broken and forces acquired their present forms. The Higgs field itself settled into its current state during the early history of the cosmos. These transitions were not necessarily destructive in the sense we imagine. They helped create the conditions under which particles gained mass and complex structure became possible. A change of vacuum can therefore be both an ending and a beginning, depending on what states exist before and after it. Some theories of cosmic inflation propose that the very early universe contained a high-energy vacuum-like state that drove a brief period of extraordinary expansion. When that state changed, its energy may have been converted into particles and radiation, beginning the hot phase of cosmic history. Inflation is supported indirectly by several features of the universe, but its detailed mechanism has not been confirmed. In some models, Inflation ends in different regions at different times, producing expanding pockets with distinct properties. These ideas lead toward the possibility of a multiverse, though that term covers many theories and remains difficult to test directly. If a broader inflating cosmos exists, vacuum transitions might continually create regions with different low-energy physics. One region could produce stars and atoms like ours. Another might have forces too weak or too strong for stable matter. Yet another might collapse quickly or expand so rapidly that structures never form. These possibilities arise from mathematical models, not from direct observation. They should not be described as known neighbouring universes. Still, they offer a useful perspective. What we call the laws of nature may partly reflect the vacuum state of our region, rather than a unique arrangement that must hold everywhere in all conceivable reality. The edge of a vacuum bubble would also raise profound questions about causality and horizons. If a transition began close enough within our causal future, the bubble might eventually reach us. If it began beyond the cosmic event horizon, accelerated expansion could prevent its influence from ever arriving. In that case, one region of a larger cosmos could undergo a complete transformation, while ours remained untouched forever. There would be no experiment we could perform to confirm the event, because no information from it could cross the expanding separation. It would be physically real in its own region and permanently absent from ours. This reveals why the phrase, "the universe ended somewhere else," can be both meaningful and misleading. A vacuum transition might destroy the familiar structures inside its future light cone, but it would not necessarily engulf all of space-time. The outcome would depend on the geometry of expansion, the properties of the new vacuum, and the location of the event. Some models even allow the interior of a bubble to collapse, while others allow it to expand into a new space-time region. Our theories are not complete enough to provide one simple picture. The word "end" compresses many possible geometries into a single emotional idea. The new vacuum might also possess a different energy density. If that energy were negative, the interior could behave like a universe tending toward rapid gravitational collapse. If it were positive, it might expand in its own way. The bubble wall could carry enormous energy, and the internal geometry might be separated from the outside by horizons. These situations require both quantum field theory and general relativity, two frameworks that are individually successful but not yet fully united. Calculations can explore simplified cases, but a complete theory of quantum gravity may be necessary to understand what truly happens at the deepest level. That incompleteness is not a failure of science. It is a map of where knowledge ends. Physics can describe particles and fields with extraordinary precision. It can describe gravity and the large-scale structure of space-time with equal power. Yet, under extreme conditions, where quantum effects and gravity become inseparable, the two descriptions resist complete unification. Vacuum decay sits near this frontier. The idea is grounded in real mathematics and known quantum behavior, but its cosmic consequences reach into territory where our present theories may be only approximations. The most honest conclusion is neither certainty nor dismissal, but carefully measured uncertainty. There is something almost peaceful in recognizing that uncertainty. The universe does not owe us a final answer before we have the tools to reach it. Our current theories may be like early maps of a coastline, accurate in broad shape while still missing hidden coves and distant islands. Future measurements of particle properties may clarify the stability of the Higgs vacuum. New physics might reveal an additional symmetry, a field, or principle that changes the calculation. A theory of quantum gravity may show that the entire question has been framed too simply. What now appears as a potential instability could become part of a deeper and more stable structure. For the moment, the vacuum around you appears calm. The atoms in the room remain stable. Light crosses the darkness according to familiar laws. The same patterns have operated across the observable universe for billions of years, allowing stars to shine and galaxies to form. That continuity is itself an astonishing fact. Every breath, every thought, and every quiet sound exists because the fields of nature occupy a state that permits complexity. We usually notice matter and overlook the space containing it. Yet the apparent emptiness between things may be one of the most important ingredients in everything that exists. So when you imagine a vacuum bubble expanding somewhere beyond sight, hold the image lightly. It is not a forecast and not a hidden event scientists believe is occurring nearby. It is a thought drawn from the deepest layers of modern theory, showing that even empty space may have a history and more than one possible state. The idea reminds us that the universe is not built only from objects. It is also built from the background conditions that allow objects to be themselves. If those conditions changed, the meaning of structure could change with them. And perhaps this is the quietest lesson of vacuum decay. The universe does not need to be shattered from outside in order for one version of it to end. A deeper state could emerge from within the fields that already fill every point of space. Yet the same mathematics that permits this possibility also leaves its likelihood uncertain and its timescale potentially beyond imagination. Tonight, nothing in the sky announces such a transition. The stars continue sending ancient light. The vacuum remains transparent and still. And the laws that hold your body, the Earth, and the distant galaxies together continue their patient work without interruption. Beyond the visible stars and galaxies lies a boundary that is not made of matter, light, or any physical wall. It is a boundary created by time, distance, and the expansion of space. We call it the cosmic horizon. Everything we observe exists on our side of that horizon because some signal has had enough time to reach us. Beyond it may lie more galaxies, more dark matter, more empty regions, and perhaps structures much like those we already know. Yet their light has not arrived, and some of it may never arrive. The horizon does not mark the edge of existence. It marks the edge of communication, the limit between what can become part of our evidence and what remains permanently outside our experience. There are several kinds of cosmic horizon, and each answers a different question. The particle horizon describes the most distant regions from which light has been able to reach us since the early universe. It sets the present boundary of the observable universe. Because space has expanded while ancient light travelled toward us, the matter now located at that boundary is much farther away than the age of the universe multiplied by the speed of light. The observable universe therefore has a radius of roughly 46 billion light-years in present-day distance. Even though the cosmos is about 8 billion years old, the distinction can feel strange at first. But it follows naturally once we remember that the road itself has stretched during the journey. The cosmic event horizon is different. It asks not which signals have reached us already, but which signals emitted now will ever reach us in the future, because the expansion of the universe appears to be accelerating. There are distant regions whose newly emitted light will never arrive, no matter how long we wait. Their older light may still be entering our telescopes, showing us chapters from their past, while their later chapters are already beyond all possible contact. This is one of the most remarkable consequences of modern cosmology. A galaxy can remain visible as an ancient image even after its present condition has become permanently unknowable to us. Imagine watching a ship sail toward a foggy horizon, except that the ocean between you and the ship is stretching as it travels. At first, messages from the ship continue to arrive. Each message is weaker and more delayed than the last. Eventually, the stretching becomes so great that later messages can never cross the growing distance. You may continue receiving old transmissions for a long time, but the ship's ongoing story has left your communicable world. In the real universe, the separation is not caused by motion through a stationary ocean. It is caused by the changing geometry of space-time. The galaxy does not need to pass a visible line. Its future simply loses every causal path leading to us. This disappearance happens gradually. Light from a receding galaxy is stretched to longer wavelengths, becoming redder and then moving into infrared, microwave, and radio bands. Its energy decreases, and the intervals between arriving photons become longer. To future observers, the galaxy would appear to slow, fade, and freeze into an increasingly ancient state. It would never seem to cross the horizon in one dramatic instant. Instead, the signal would become so faint and so widely spaced that detection would eventually become impossible. The galaxy would not have been destroyed. It would have been removed from our future knowledge by expansion, becoming silent not because nothing happens there, but because nothing happening there can still reach us. The process does not affect all galaxies equally. Nearby galaxies bound together by gravity can resist cosmic expansion on local scales. The Milky Way, Andromeda, and many smaller galaxies belong to a gravitationally connected region called the local group. These systems will continue interacting and may eventually merge into one larger galaxy. More distant groups and clusters, however, are not gravitationally bound to us. Over immense periods, accelerated expansion will carry them farther away, beyond any possibility of future communication. The observable universe will grow emptier from the perspective of our descendants, not because matter disappears, but because fewer regions remain causally connected to their location. This creates a peculiar situation. A civilization in a remote galaxy could exist at the same broad cosmological era as we do, study the universe, and ask questions similar to ours. Yet if enough expanding space separates us, neither civilization could ever know that the other exists. Their signals would travel faithfully at light speed and still fail to bridge the growing distance. Each civilization would inhabit its own observable region, surrounded by evidence drawn from a different cosmic sphere. Their sciences might uncover similar laws, but their skies would contain different histories. The universe could be filled with observers who are not merely far apart, but permanently excluded from one another's reality. Such isolation places a limit on the dream of exploring the whole cosmos. Even a spacecraft moving arbitrarily close to the speed of light could not reach every galaxy visible today. Some destinations are already beyond our future reach because space expands too rapidly between here and there. As time passes, the number of accessible galaxies decreases. This does not make interstellar travel within our local region impossible in principle. Though the distances and engineering demands remain immense, it means only that there is a larger boundary no engine can overcome. Technology can approach the speed limit set by nature, but it cannot defeat the geometry of an accelerating universe. The horizon also complicates the idea of a cosmic ending. Suppose a distant region undergoes vacuum decay, collapses into an unusual state, or simply evolves until its stars fade. If that region lies beyond our event horizon, the change can never affect us. From our perspective, it belongs to no observable future. We may still receive light showing the region before the event, but the final outcome remains forever hidden. In that sense, something may have ended beyond us without leaving any possible evidence here. Science cannot confirm or deny a specific unobservable event. It can only describe what kinds of events are allowed by theory and what boundaries prevent their signals from reaching us. This is where scientific humility becomes essential. A claim about an unreachable region cannot be tested directly. We may infer that the universe probably continues beyond our observable horizon because the large-scale cosmos appears smooth and because there is no reason to expect existence to stop exactly at our limit of sight. But we do not know the full size of the universe. It may be finite or infinite. It may curve back upon itself on scales far larger than we can observe. Or it may extend without bound. Measurements show that observable space is very close to geometrically flat. Yet small curvature across a much larger whole remains possible. The horizon hides not only distant objects, but the global shape of reality. Inflation, a proposed phase of rapid expansion in the very early universe, offers one explanation for why the observable cosmos appears so uniform. Regions now widely separated may once have been close enough to exchange energy before inflation stretched them apart. This could explain why the cosmic microwave background has nearly the same temperature in every direction. Inflation also suggests that the entire universe may be vastly larger than the region we can see. However, the detailed physics of inflation remains uncertain. Scientists have strong reasons to study it, but no single model has been conclusively established. It provides a framework for thinking about the unseen cosmos, not a final map. If inflation occurred, there may be regions so distant that their present state has never been causally connected to ours since the earliest moments. We cannot assume that every part of the entire universe looks exactly like the portion we observe, although large-scale uniformity is a useful working principle within our horizon. Beyond that, conditions might be similar, or they might differ in ways no signal can reveal. Some speculative models imagine domains with different field configurations or physical constants. These ideas are mathematically motivated, but unconfirmed. The honest scientific position is that the space beyond our horizon may be vast, yet our confidence decreases as our claims move farther from observable evidence. Even within the observable universe, we see different regions at different ages. The farther we look, the earlier the image. This means the distant cosmic horizon is not a shell showing what those places are like today. It is a shell showing ancient conditions. We cannot directly compare our present with the present of a region billions of light years away. We compare our present with its past. Cosmological models bridge the gap by predicting how structures evolve. But observation always remains anchored to the incoming light cone. The universe available to our eyes is therefore a history arranged by distance. While the universe described by theory includes many present states that no telescope can yet reveal, there is a quiet paradox in this arrangement. As time passes, the particle horizon can expand because light from previously unseen regions may finally reach us. Yet the event horizon limits which new signals will ever arrive. We may gain access to some older information while losing access to the future of sources already known. The archive grows in one sense and closes in another. More ancient light completes its journey, while accelerating expansion seals off later chapters. The universe does not simply reveal more of itself with time. It reveals some histories while permanently withholding others, turning cosmology into the study of both discovery and disappearance. A far future civilization within our gravitationally bound region might face a much lonelier sky. Distant galaxies could have redshifted beyond practical detection. The cosmic microwave background would be stretched to extraordinarily long wavelengths and become difficult to measure. Evidence for the expansion and hot, early state of the universe might be obscured. Those observers could develop brilliant science and still struggle to reconstruct facts that are obvious to us today. Our era may therefore occupy a special observational window, not because we are cosmically central, but because ancient evidence remains visible while many distant galaxies are still detectable. This thought gives new meaning to every deep image made by a telescope. A faint galaxy is not merely an object at a great distance. It is a temporary connection between regions that may one day become permanently separated. The photons arriving now left before anyone on Earth could receive them, crossed an expanding universe, and entered an instrument during a narrow era in which they could still be detected. In the distant future, newer photons from the same source may never arrive. Astronomy records these fading relationships. Preserving knowledge of a broader cosmos before expansion carries much of it beyond all observation. The horizon does not surround us because Earth occupies a privileged place. Every observer, wherever they are, has a horizon centered on their own world line. A distant galaxy possesses its own observable universe, overlapping with ours in some regions and extending into regions hidden from us. The whole cosmos may be thought of as countless local views, each incomplete, each centered only by perspective. No observer sees everything. No location receives a universal panorama. Reality is larger than any one light cone, and perhaps larger than the combined reach of all observers who could ever communicate with one another. This limits what science can know, but it does not diminish what science has achieved. From one small planet, using light, mathematics, and patient observation, we have reconstructed a history extending back billions of years. We have measured the expansion of space, traced the growth of galaxies, detected the afterglow of the early universe, and identified horizons that no physical journey can cross. The boundaries of knowledge are not failures at the edge of the map. They are discoveries about the map itself. Knowing that some regions are unreachable is itself a profound form of understanding. And so, if the universe has already ended somewhere else, it may have done so beyond every possible message. A star may have gone dark in a galaxy whose future light will never reach us. A civilization may have risen and vanished outside our causal horizon. A vacuum transition may have transformed a domain permanently disconnected from our own. None of these possibilities can be confirmed without evidence, and science must leave them uncertain. Yet the geometry of the universe allows something quieter and more certain. Many places will continue their histories after all contact with us has ended. As you let that idea settle, imagine the cosmos as an ocean of islands slowly drifting apart. For a time, lights can be seen across the water, messages pass between shores, then the distances widen, the lights redden, and the waves carry fewer signals. Eventually, each island keeps its own night beneath its own horizon. Nothing needs to be destroyed for the separation to become complete. The universe can continue everywhere while becoming divided into regions that can no longer share their futures. And within our own small island of causality, the ancient light still arriving is enough to remind us that we once belonged to a wider visible sea. After travelling through delayed light, relative time, stellar death, vacuum decay, and the quiet borders of the observable universe, we return to the original question with a different sense of what it means. Perhaps somewhere, something has ended. A star may have collapsed. A civilization may have vanished. A galaxy may have faded beyond contact. Or a distant region may have crossed into a state we cannot imagine. Yet the universe does not present these events to us as a single final verdict. It presents them as scattered histories, each carried by signals, each bounded by causality, each known only when nature permits the evidence to arrive. The deeper mystery is not whether endings exist. It is how many realities can continue beyond the edge of one another's knowledge. From Earth, we live inside one small cone of available information. The night sky is a layered memory, not a view of one universal present. The moon appears moments ago, the sun minutes ago, nearby stars years ago, and distant galaxies in ancient stages of their lives. The farther we look, the more deeply we enter the past. This means that our picture of the cosmos is always incomplete, but it is not false. It is a faithful record of what reached us. Every photon offers one true piece of a larger story. Even when the later chapters remain hidden, the universe is not withholding a complete image that exists somewhere outside us. A complete image of one shared cosmic now may not exist in the simple form our intuition expects. This changes the emotional meaning of uncertainty. We often treat uncertainty as a gap that ought to be filled, a temporary inconvenience standing between us and the final answer. But some uncertainty is woven into the geometry of the universe. No telescope can receive a signal before it arrives. No observer can see beyond every horizon. No experiment can directly test an event that is permanently outside causal contact. These are not failures of imagination or technology. They are physical limits. And yet science does not become powerless at those limits. It becomes more precise. It learns to distinguish observation from inference, possibility from probability, and meaningful speculation from unsupported certainty. That discipline matters when we ask about endings. We know that stars exhaust their fuel because we observe many stages of stellar evolution and understand the nuclear physics within them. We know that galaxies change because we compare structures across cosmic time. We know that black holes create horizons because general relativity has survived demanding tests, and observations reveal objects behaving as the theory predicts. We know the universe is expanding because light from distant galaxies, the cosmic microwave background, and the distribution of matter all support that picture. Vacuum decay, by contrast, remains a theoretical possibility rather than an observed event. Science preserves wonder by allowing each idea to carry the level of confidence it has earned. The title may sound as though the universe is one enormous machine that could stop in a distant room while our own part continues running. But the cosmos is not divided so neatly. What ends depends on what structure we are following. A star can end as a source of fusion while continuing as a remnant. A galaxy can end as a vigorous nursery of stars while remaining gravitationally intact. A planet can end as a habitable world while orbiting for billions of years afterward. Communication can end across a horizon while both sides continue existing. Even the far future heat death of the cosmos would likely be a gradual loss of usable differences. Not a single instant in which existence is switched off. There is something deeply natural about this. On Earth, too, endings are usually transformations rather than absolute erasures. A fallen leaf becomes soil. A mountain becomes sediment. A species disappears. While its genetic history survives in relatives and its ecological effects remain in the landscape, human lives end. Yet words, choices, and memories continue through other people. The cosmos operates on scales far larger than these familiar examples. But the pattern is similar. Matter changes form. Energy spreads. Structures arise for a time, then pass into other structures. The universe is not preserved by resisting change. It is made visible through change. Our own existence depends on many ancient endings. The carbon in living cells was forged inside stars. Much of the oxygen we breathe and the silicon in rocks came from earlier generations of stellar fusion. Some heavy elements were produced in violent events such as supernovae and neutron star mergers. The solar system formed from material enriched by stars that had already completed their lives. In that sense, we are not merely observers of cosmic endings. We are assembled from their remains. The atoms carrying your thoughts tonight have passed through histories older than Earth, and perhaps through environments no human mind could fully reconstruct. This does not mean the universe was preparing for us, or that every destruction exists for a later purpose. Science gives us no evidence that cosmic history was arranged with humanity as its intended destination. Most of space is hostile to life as we know it. Most stars will never illuminate an inhabited world, as far as we can tell, yet purpose is not required for connection. The fact that our bodies participate in the same physical history as stars and galaxies is already profound. We belong to the cosmos not because it was built around us, but because there is no separate material from which we could have been made. For most of human history, the universe appeared smaller, younger, and more centered upon our world. The stars seemed fixed upon a nearby sphere. The Milky Way looked like a pale river across the sky. Only gradually did observation reveal that the Sun is one star among hundreds of billions in our galaxy, and that our galaxy is one among countless others in the observable universe. Each expansion of scale might have made humanity seem less important. Instead, it gave human curiosity a larger home. We are physically small, but we can understand processes that operate across billions of light years and billions of years. That ability is itself a natural event. The brain listening to these words is made of matter following the same laws as distant nebulae, yet it can form an image of the observable universe. A small biological organism on one planet can infer the existence of horizons it will never approach, stars it will never visit, and eras long before life began. Our understanding is incomplete and sometimes mistaken, but it is not trivial. Through measurement and reasoning, one part of the universe has become capable of reflecting upon other parts. The cosmos, through us and perhaps through other minds elsewhere, has developed local islands of awareness. We do not know whether those other islands exist. The universe contains an enormous number of planets, and many may possess conditions suitable for complex chemistry, but the origin of life remains incompletely understood, and the emergence of intelligence may be rare, common, or dependent on circumstances we have not recognized. Searches for life beyond Earth continue, but no confirmed evidence of extraterrestrial biology or civilization has yet entered our possession. The silence may reflect distance, rarity, timing, technological differences, or the limits of our search. It may also remind us that the universe can hold many possibilities without revealing which one is true. If distant minds do exist, they may look into a sky arranged by a different past light cone. They may see galaxies hidden from us and miss regions visible from Earth. Their constellations, cosmic history, and local dangers would differ. Perhaps some live in a region from which our galaxy has already faded beyond practical detection. Perhaps others have not yet received light, showing that Earth has formed. There may be worlds whose telescopes display the cloud from which the sun will eventually emerge, while the beings observing it are themselves forever beyond our horizon. Such images are speculative, but they follow a real principle. Every observer inherits a different archive of light. This is why there may never be a final observer who knows what happened everywhere. Even an unimaginably advanced civilization would remain inside some causal structure. It might build vast instruments, travel between stars, and preserve knowledge for ages. But it could not collect information from beyond every event horizon. No intelligence can stand outside space-time and inspect the entire universe at once. Knowledge must always arrive along a path. It must be carried, recorded, compared, and interpreted. The universe allows understanding, but it does not promise omniscience. Perhaps wisdom begins when curiosity accepts that difference without losing its desire to learn. The question of whether the universe has already ended somewhere else, therefore, becomes less like a warning and more like a meditation on perspective. Somewhere, old structures have certainly disappeared. Somewhere, new stars are forming from cold clouds. Somewhere, planets are circling suns whose light will not reach Earth for ages. Beyond our horizon, events may be unfolding that can never enter human history. Yet here, in this region, the universe remains active. Light still arrives. Atoms still combine. Life still notices the darkness and asks what lies within it. The hidden fate of distant places does not make our present unreal. It makes our present local, temporary, and precious. There is another reason endings seem to have a direction. In ordinary experience, broken cups do not reassemble. Smoke does not gather itself back into a candle, and memories point toward the past rather than the future. Physics describes this tendency through entropy, a measure related to how many microscopic arrangements correspond to a visible state. In an isolated system, entropy is overwhelmingly likely to increase. This statistical arrow of time helps explain why stars burn fuel, why heat spreads, and why complex structures require flows of usable energy. It does not predict one dramatic final second. It describes a gradual movement from concentrated possibilities toward more evenly distributed states, while local pockets of order can still arise along the way. Our place within that process is neither central nor meaningless. Human beings occupy a brief interval when stars shine. Planets can remain warm, and the universe contains abundant differences in energy from which life can grow. What we do with that interval matters locally, where causes can still meet effects. We cannot protect every distant galaxy, or prevent the ultimate evolution of the cosmos, but we can care for the small region entrusted to our influence. Knowledge of cosmic limits need not produce indifference. It can sharpen attention, reminding us that habitable worlds, living ecosystems, and conscious moments may be rare achievements of matter. Even if nature produced them without a predetermined plan, there is no need to carry the whole cosmos tonight. You do not need to solve the meaning of time, picture every galaxy, or decide which speculative future will occur. It is enough to rest within one small part of space-time, on a planet turning steadily beneath an old and generous sky. Above you, photons are completing journeys that began before human language. Around you, the fields of nature remain calm enough for matter to hold its form. The ground supports you, the atmosphere moves softly, and Earth continues along its path around an ordinary star whose light has sustained nearly every life you have known. Perhaps somewhere else, a story has ended. Perhaps somewhere else, another is only beginning. The universe is wide enough to contain both without contradiction. It does not move toward one emotion or one conclusion. It unfolds through countless local changes, some luminous, some violent, and many almost unimaginably slow. We receive only a small portion of this unfolding, but that portion has carried us from ancient radiation to galaxies, stars, planets, oceans, cells, and awareness. For a brief time, we are here to notice it. Then we, too, return our borrowed matter to the continuing world, leaving new arrangements where our own patterns once briefly held together. And now the question can grow quiet. Has the universe already ended somewhere else? It may have, in one of the many meanings of ending, but no distant silence erases the light arriving here. No hidden horizon takes away the reality of this moment. The cosmos does not need to be complete in our understanding for us to belong within it. Let the unanswered regions remain beyond the edge of thought, not as threats, but as dark shores under unfamiliar stars. Let the old light continue crossing the night without hurry, and as Earth turns beneath it, allow your own thoughts to slow, soften, and drift into the peaceful distance.